Can you see me? Good. Okay. Welcome everyone to the Winter EM course. Today's lecture will be Reza Khayat. He received his bachelor's from the University of California, Irvine, and his master's and his PhD from Columbia University. Reza is currently an assistant professor at the City College of New York, where he's using Cryo-EM to study the life cycle of DNA viruses at atomic resolution. Reza's lecture today is titled Single Particle Analysis Part 2, Data Analysis and Reconstruction Workflow. For those joining us on YouTube, please feel free to ask any questions over the YouTube chat, and similarly those inside the classroom. This is a fairly interactive and informal classroom setting, so any questions you have, feel free to pick Reza's brain. So there we go.
All right, thank you so much, Laura. Thank you for the opportunity. So I'll stand here closer to the microphone, hoping that the YouTube crowd can hear me. And if you take a look at the lecture really quickly, it's fairly short, I think 18 slides. And the idea here is to get three things happen. One, hopefully you guys watched the Grant Jensen lecture, and you guys have somewhat of an idea of what's going on with the microscope. Two, you'll have lots of questions, whether it pertains to your project or whether it has something to do with what I said. And three, I'll actually be able to answer your questions. So those are the three things I'm hoping to get accomplished here. Okay, so again, let's try to make this into more of a discussion rather than me just giving you a fairly short lecture. Okay, so you guys have already heard all the theory, not the theory, but the hardcore material from Joachim Frank about microscopy, Fourier transforms, image formation, image correction, all that stuff. So we're going to take, this is going to be more of a workflow, more like how do you essentially go about start doing the microscopy, and how do you do the single particle analysis. So obviously in the beginning you've got the sample preparation. You want to make sure you have good sample. I know it's really easy that finally when you get some sample you start thinking, screw it, let's put it on the grid, let's see what it looks like, and let's just collect a million particles and I'll get this structure. Unfortunately, that doesn't work. I've been told that a bunch of times. I tried it myself. It just doesn't work. So number one is make sure your sample is clean, make sure it behaves well biophysically, make sure you have a good concentration. You generally want something from 0.1 micron to 10 micromolar for cryo-EM. Again, this is sample specific. Some samples love to stick to the grid, to the carbon substrate. Others love to go into the hole, very photogenic, and they look great when you take images. And then there's different types of grids you can use for addressing this problem of whether your particles go into the holes or whether your particles stick to the substrate. The buffer is obviously important because that's where your contrast comes from. If, for example, you have a lot of glycerol, sugar, anything that gives you additional type of scattering in the background, you're going to diminish the contrast from your particle. So ideally, you want it in something like water, right, where you have the greatest contrast. But then that also in itself creates some problem where you start having particles aligning on the air-water interface. And a lot of proteins don't like being in water, right? They want some sort of solute present. They want maybe at the very minimum salt, some like neutral pH, some like alkaline, others like acidic pH. So these all obviously you'd have to identify as you're preparing your sample, see what works best. And
Sorry,
yeah.
could you move a little bit to this side?
Okay.
Perfect, thank you.
And then if there's also issues that when you freeze your samples, they will break. The freezing condition happens to, by all biophysical methods, the samples look great. You have 10 different ways that you looked at your sample, everything looks good. You make a cryogrid and everything's just in pieces. I think it's just, I think the freezing itself ends up being a bit destructive. Again, this is sample preparation, this is part of the sample preparation, and there's solutions for this. For example, graphics allows you to establish a gradient of cross-linkers, and this will essentially, you run this, you put your sample, you run it through this gradient. I think you can do it with ultracentrifugation, and you essentially cross-link your sample, and then you freeze that sample in the hopes of keeping your sample from flying apart.
Question
Yes.
from YouTube. So this is from Zainab. What do you do if your particles stick to the grid? I'm assuming he means to the carbon and not to the
Sure.
holes.
So there's different ways. So the Wiesler group a couple of years ago essentially came out with a nice way of applying multiple samples to the grid. For example, 3 blots. You put it 4 microliters on there, you blot it off. You put it on another 4 microliters, you blot it off. A third time, blot it off. And then I think on the 4th time, or maybe on the 3rd time, then you plunge freeze. That's one way where you saturate the carbon substrate with your sample so that your sample has nowhere to go other than inside the hole. And according to him, he has great success with this. Alternatively, you can try other types of grids where I think with gold, we've had some success where samples, because of gold, it's a noble metal, particles aren't supposed to stick to it, and particles are essentially ushered into the ice. So those are 2 ways of dealing with it. And I think if you read through the literature, there's a bunch of additional ways. But I really like David's method because you don't have to try a bunch of different crazy stuff.
Sure.
It seems like it plugs into to the regular workflow and it works.
You just need more sample.
You just need more sample, exactly. Okay?
Thank
Other
you.
questions? Okay. So grid preparation, obviously you want to start off doing a negative stain, right? It's not the most exciting way of doing it. You don't jump ahead and go into ice, get to that nice atomic resolution, but it's something, again, you have to do. And again, to me, this is part of the sample preparation. How does it look like with negative stain? Do you see single particles or do you see things aggregating? Can you calculate 2D class averages from these? And obviously you have to play around with the different types of stains. Some stains, like for example urinal acetate or urinal formate, have a low pH around 4. So if you treat your sample with these things, and I know, for example, hemagglutinin does this, it'll undergo a conformational change, and then that's going to start affecting your results. So you have ammonium molybdate, you have phosphotungsten acid, nano-W, nano-Van, which are all neutral pH stains. So try these stains, buy these stains, try them out, and you want to really, at the end of the day, get a nice particle distribution. You want to see good 2D class averages and try to at least get into 3D, get some sort of a 3D reconstruction. This gives you an idea of what do I start out with, and is it actually freezing that starting to cause some problems? Or do my particles just look like mediocre to begin with, okay? And then grid plotting, when you finally do get into the cryo, again, some groups, I think Gabe Landers go with the manual method. I think when he said it, I thought this was silly, but I mean, he gets, his entire grid looks gorgeous. So it's not the easiest way of doing it. It becomes an art. It takes a lot of practice, but his guys are getting these gorgeous grids left and right. So it's something worth trying. You can try, obviously, the VitralBot. You've got all these different types of robots. You've got the Gatan CP3. You've got the Leica instrument. And each one has a slightly different advantage and disadvantage to it. You can also try spraying. There's this time-resolved spray plunger. I don't use that. And then we've tried Spotted On, which was developed here, and now I think it's being commercialized. And this essentially uses the idea behind inkjet technology and shoots your sample as your grid is dropping and going into ethane. So you get a very nice thin layer of ice forming along the grid, and then you get a very thin layer of ice in there as well. And I think depending on the way it goes, the grid goes in, you also get somewhat of an ice thickness going. It varies from one end to the other, so you can get your particle distribution can be a little bit different. It's extremely useful for situations where you have particle orientation preference. I think when you have situations where particles essentially get stuck in the air-water interface, it's also had good success with that. So again, trying these different things will actually end up helping the data processing at the end, because if garbage goes in, garbage comes out. I've spent a lot of time processing garbage, and it's just, you end up burning a lot of time. You try a lot of different things, but it just doesn't work out. That doesn't mean not to try it. Try it because at least you understand what's going on. You understand what garbage is. Having said that, then you have different types of grids. I talked about a carbon substrate. I talked about a gold substrate. I think there's additional substrates out there as well. But you also have different types of gold hole sizes, right? If you look at protochips, or if you look at EMI, you can buy different types of grids with different hole sizes. And again, the hole sizes can make a difference. You also have these additional types of grids that I keep forgetting what the names are, but the holes are irregular. And on the back, you can buy these from Ted Pella, and on the back there's a very thin layer of carbon. we've had success with this. If, for example, if you have big megadalton-sized particles and you can't get these to a high enough concentration, you can at least absorb them to the grid, to the carbon. And because the carbon is small and you have a big particle, you can get enough signal to get you down to below better than 3 angstrom resolution. So this is possible. Smallest thing we tried it on was the 1.5 megadalton, but I'm pretty sure it'll work with something like 700, maybe 400 kilodalton. We tried it with something with 225, it didn't work out very well. You can see the particles, but the alignment didn't go out, so it didn't work out that well. So then you also have these affinity grids, right? With the affinity grids, for example, you could have a lipid with a nickel at the end, and if you have a protein with a histag on it, you bind your protein to the grid, you incubate them, the his interacts with the nickel, and it's like affinity purification, and then you have a concentration of your sample on the grid. You freeze that, and now you increase your particle count. Okay, so there's many different ways of increasing the count of particles on a grid, and there's many different types of grids you can use. And the grid I was thinking of was LACY, L-A-C-E-Y. Okay, so in certain projects, I know that LACY grids will work, whereas quantifoil, C-flats, and other types of grids don't work. So that should also be in your toolbox.
Question.
Yes.
So when you get started, what is your usual go-to? Like when you're going from negative SEM to cryo, what is like your starting point? Is it just like a C-flat?
I go with the C-flat.
Okay.
Because these are
you don't just go straight to gold or anything.
No, because C-flats are cheaper, and if you can get good power spectra coming off of a C-flat, great. It also depends on how much sample you have. Like for example, if we don't have that much sample or the concentration isn't that high, then we'll go to a gold. Okay. One of the things, the difficulty with gold is that the grids are great, and you can buy the grids, which makes them even easier. The problem is when you put in the order, that it tends to be back ordered for quite some time. So because of that, we're a little bit cheap with using these things, because if we run out, then now I gotta wait 2 months, and now everything slows down.
That's pretty good. Sometimes we're back ordered like half a year.
Yeah. So we've been getting lucky, but this is something we have to worry about. Okay, and it's also the cost. Gold grids the cost a little bit more, and it also depends on the expertise of the individual. If the individual is just learning how to do it, don't waste the gold grids, because the first set of grids you're going to freeze, they're just going to get bent. Start with something that's a little bit cheaper. The C-flats are more accessible, and then once you've mastered it and you think you can do it in your sleep, then move ahead to the gold grids. Okay? Okay, so screening and data collection, some of the stuff I talked about already. Obviously, generate the 2D class averages and possibly the 3D reconstruction and stain to make sure that your particles are good. You have a high signal to noise ratio, and see if you can't get it to work in stain, most likely you're not going to be able to get it to work in cryo, but I have heard situations where it does work. So if you're working on an extremely important project, on a hot project, you got to give it everything you got, right? At the end of the day, the only thing that's left is I tried everything I could, and it didn't work. Not that, oh, you know what, I don't think this is the best way of doing it. Don't hold back, right? The last thing you want to do is hold back and get scooped because someone else was not holding back. And then after that, obviously, you start going into ice, and if you generate 2D class averages, and who's going to wait? You're not going to go to the 3D part, right? So once you're in ice and you can generate good 2D class averages, then it's just a matter of time before you get the reconstruction, okay? Unless if you have a serious orientation problem, and there's now solutions that can address this as well. Try to collect more than 100,000 particles. If you guys have a Cryo session here at the NYSPC with the insanely fast data collection strategy that's been set up here, you can collect lots and lots of images. And getting to 100,000 good particles should not be an issue at all, right? Unless you have big particles and you see one in your hole per hole, then in that case, go back and increase the particle. Don't waste people's time, okay? Because there's lots of users that use the facility, and you guys are extremely fortunate to have the expertise here as well. Okay, so what kind of microscope you want to use it on? 300 kVs are fine. There are labs that are doing beautiful work with 200 kVs as well. So at this point, I would say at 300 if you're doing tomography on cellular thin sections, at 200 kV is good enough for doing high resolution single particle analysis work. And obviously a direct electron detector, because you want to do frame alignment and drift correction. Okay? So data collection strategy. This is a little bit outdated because nobody really does this stuff anymore. But you all, everything obviously started out with manual. You had a low dose kit where you would focus on a particular part of the grid that's right next to the hole you want to image. Then you would tell the microscope to take an image of the hole, and the microscope would go to a predefined defocus value after you establish the focus, and it would take the image. And that's called essentially the low dose kit. You had 3 settings, if I remember correctly. You had a search, a focus, and an acquisition. Okay? Again, nobody does this anymore, and now you have multiple different types of programs to do the data collection. The 2 popular ones are obviously Leginon and Cryo-EM. Leginon having been developed by NRAM, Cryo-EM being developed by Boulder, Colorado. You also have UCSF Image 4, FEI's version of Leginon, which is FEI EPU, which I think EPU stands for Many Comes One. And then you have Jail's adaptation of Leginon. And I think this is probably the least developed, but I think with Jail coming out with the new instruments, it's going to be developed even more. Or they have a completely different type of data collection strategy or algorithms. Okay, so you have manual versus automated data collection.
There's also Gatan latitude.
I was not aware of that. There's Gatan latitude. Thank you for that. Is that a new one?
They've been betaing it for a while, but
okay.
It's not.
Okay. Okay. Well, no opinions. There's Gatan latitude out there as well. And I assume this comes with the K2s.
I'm not sure.
Okay. All right.
Yeah.
Well, the K3s. Okay.
That's
you can.
UCSF,
Okay.
last I heard, yeah.
Okay. So then with the data collection strategy, and again, as with everything goes, as with crystallography there's many different strategies, and all of them seem to be working. And I think at the end of the day, you can use many different ways to get at your structure, but at least this seems to be converging on one theme. And over here at the NYSPC, I think you have a default data collection where you can generally take 1 image per hole, but you can take several. You can adjust your dose rate, essentially how fast the electrons go down the column or how many electrons you get per second. The total amount of dose that you have, which is it's depending on your dose rate, determines how much data, how much time you spend per image collecting data or images per hole. You have the number of movie frames. You can collect, for example, a frame every 200 milliseconds. If you collect 5 seconds, that's 5 times 5, that's 25 frames. You have wait time between moves. I think here, with the fast data collection strategy, and I may be wrong, it tends to be more of an image shift. So you're not moving that much. You move to one square, and then you take a whole bunch of images. Okay, so this essentially diminishes the amount of wait time, and this is one of the reasons why you're collecting at such a fast or accelerated rate. And then you have frequency of focusing. The advantage of doing a lot of focuses is that you can control the defocus value a little bit more. But if you take 1 focus per square, essentially your square is rarely ever going to be flat, right? So if you take 1 focus point, you can actually use the variability in the square to actually increase the number of defocus values that you collect at. So you can use that as a strategy, spend less time focusing and more time collecting data, and essentially get a broader range of defocus values. Okay? So here's essentially one, yes?
So what are the advantage of doing images, 1 image per hole and many images per hole?
So the advantage of doing many images per hole is that you get a little bit more data out, right? But sometimes it happens that you're near the perimeter of the hole, you might have thick ice, in the center you have thin ice. So you might have to take an image right in the center, just so you can get thin ice and you can get a good power spectrum, you can get good signal to noise ratio, and that way your data is more processable. Other times you have holes that are small enough that you can't collect multiple images on, because there'll be overlap, and essentially by collecting on one spot, you'll destroy things that were not imaged in the neighboring, in the vicinity.
So how does this compare to like tomography, where you get many images per?
So with tomography, you collect tilts. Right. You go over one spot, you collect very low total dose or very low doses per image, about 2 electrons per angstrom squared. But with a single particle analysis, you essentially hit it with something like 40 to 70 electrons per angstrom squared. Right. So each exposure in single particle analysis gets a lot of dose, was in tomography it gets a lot less dose because you want to essentially distribute that entire dosage across all of the images that you're collecting with tomography. Yes?
Another question. Sorry, did that answer your question?
Yeah.
Okay. From YouTube, this is from Kupju. Do you have to consider smaller beam size and also magnification when collecting several images per hole? And you might want to also comment on like the parallel range, right? Like so, for a parallel range on a Krios, it's typically for a 1 angstrom per pixel, anywhere from 0.7 microns up to like I think 5 microns.
Yeah.
But so you want to be within that range to have a parallel beam. So if your hole size is like 1.2 C flat, right, or 1.2 micron hole, and your parallel range of your beam, and you have it at like 1 to 2 microns illuminated diameter, you can only image one exposure per hole because your beam is covering that entire hole itself. So you can't like do multiple hole like images per hole. But also, yeah, smaller beam size and magnification. So if you're at higher mag, right?
Yeah. Yeah. So there's a lot of things that go into the data collection strategy, right? And then depending, some of these things vary from one scope to another as well, a little bit. So it's best to get the expertise of the individuals that know how the scope behaves to see what the best data collection strategy will be. Okay?
Yeah, thanks.
And I think Laura did an excellent job answering some of the earlier questions as well. Okay? Okay. Other questions? All right. Okay, so this is generally one of the routines or a generic routine that we use for single particle analysis. You're going essentially through different steps here, and again, this can vary. Some labs use slightly different strategy, but essentially this is all of the things that go into a workflow. You obviously start with your data collection. You're generally going to be collecting in counting mode on one of the detectors. You want to start off with frame alignments. The strategies for frame alignment are a little bit different. We do the frame alignment here because the majority of the data we collect is at the NYSPC. We do also collect data at the ASRC. The frame alignment is done, if you're collecting here, it's done here. There's plenty of GPUs. Some people like to throw out the first frame because they say that causes the most drift. Others would argue, well, that's where the majority of your high frequency signal is, so why would you want to throw out the first frame? You can keep all the frames and you can play with it however you want. There's also movie mode and Rely On where you can play around with the different strategies to improve your reconstruction. And then there's particle identification and CTF estimation. So this is essentially drawn linearly because you have to do collect data and then do frame alignment, but you can do, for example, particle identification and CTF estimation at the same time, right? The two, you don't need to complete one task to go on to the next task. So these two you can parallelize. In the CTF estimation, many different programs. I'll talk about some of these programs in slides to come. And then particle identification, again, you can use templates, which are 2D class averages or projections that you may have already have on the particles. Or you can use a difference of Gaussian or blob picking to pick particles from your micrographs. Then you have your particle extraction and your CTF correction. So I put this here because we used to essentially do CTF correction phase flipping on the micrographs themselves. And sometimes this is helpful. Still nowadays we have some data set where this works. But generally CTF correction is now done doing 2D classification, 3D classification, or 3D refinement. Okay, so it's done under the hood. But at this point, what you want to do is you want to take all the micrographs where essentially you have poor CTF estimations, meaning either you have you have wacky numbers for your defocus values, or whether you have low figures of merits or low correlation coefficients for the estimation of your defocus value. And you want to essentially filter those out and essentially take the best micrographs that you have. Okay, you can also look at your tone rings. And you can see, okay, based on my tone rings, is this worthwhile processing or not? And again, here an additional, not necessarily new, but a recent addition is the use of ice thickness. Okay, so now there's routines for measuring how thick your ice is. So you can use that as a strategy to filter out whether you want to kip a particle or not. So for example, you can say, I'm only going to work with micrographs that have from 20 nanometer to 150 nanometer or 100 nanometer ice. Anything else, I'm going to throw out. So you collect a bunch of data and you start filtering based on different types of criteria. And which criteria you should use really depends on what your aims are, what your question is you're trying to address, how big your particles are, and really how desperate you are for getting any sort of reconstruction out. You could sort particles. This was a routine that XMIP would do, whereas essentially you're looking at the intensity of the particle with respect to the background. You could do a normalization, do z-scores, see which particles are worth keeping or which not. Or you can just extract the particle, and generally what we do is I extract the particles and I bin it to a size by 64 by 64, regardless of how big the particle is, and then I feed that into 2D classification. I do that for the simple reason that it just expedites the entire process downstream significantly. Right? So I bin it 60 by 64 to 64. Doesn't matter how big the particle is. You feed that into 2D classification. You get 2D class averages extremely fast. If you have 1 million particles, you can blast through them in a day or so. And then you can generate your model. You can do your 3D classification. You can further enrich the particles, your data set for good particles. And then you can go back and you can re-extract just those particles from the micrographs at full size. Okay? And then you can take that and you can push the resolution of that. So that's just done to expedite the entire process. Okay? So you do your 2D classification, you generate your model. There's a couple different programs for doing this. I'll talk about that in slides to come. And then you can go into 3D classification. Now, not all labs go this way. And we have some data sets where we go from particle extraction straight into 3D classification. Okay? The reason for this is that if you have rare views that tend to get lost during 2D classification, for example, Reliant goes, oh, this is 0.0001% of the data, it gets thrown in with the junks, then you want to go into 3D classification, and that actually helps enrich those rare views. And those rare views are obviously going to be extremely important, as you'll see near the end of the talk, when you start having problems with anisotropy. Okay? So you can go this route, enrich those rare views, and then go back into 2D classification to purify it a little bit more. Okay? Then you get good 3D class averages, and if you have, sometimes it happens that one class goes to high resolution and a bunch of them don't go to high resolution. And we have some examples we'll have one example, I'll talk about that. Other times you have classes that multiple go to high resolution and they all look a little bit different, right? And if they look a little bit different, if you have conformational variability, you take each class and you do 3D refinement on that. You push the resolution. Again, at this point, you might want to go and extract particles at the full size. Then you can do 3D, you can do CTF per particle. This is a part of Reliant 3's capabilities. You can improve the defocus values and then do 3D refinement again, and you can keep repeating this part until the resolution stops improving. Okay, so you do per particle CTF estimation, and then you can feed this into focused classification. Okay, focused classification, there's many different ways of doing this, many different programs, but essentially what you're doing is you're putting a mask over a region that you think is variable, whether it's conformationally variable or configurationally variable, meaning one subunit is present in some data, in some of the particles, and it's not present in the others. So you put a mask over that one region, and then you start classifying based on that, and you pull out data, or you identify particles that either have a subunit or they don't, or if a particular region is flexible and it's moving around. Okay?
Doesn't that also hold to like membrane proteins where it's like over-aligning on a micelle?
Yes. So the over-aligning on the, yes, so you can use that to classify that way as well. So focused classification essentially is using a mask to classify in a particular region, and you can get creative with it and use it for many different methods, right? It's just a tool. So you don't have to restrict yourself to conformational or configurational variability. It's a tool, use it for whatever creativity your creativity allows you to use it for. Okay? That's how all of these things are. And now you have multi-body refinement that Reliant 3 allows you to do, and essentially that's looking at this motion that you might have, for example, in the ribosome or some in the spliceosome, and there's again limitations to that as well. So after you classify everything, after you get to a high enough resolution, you obviously have your model building, refinement, and then you can do your site-directed mutagenesis, biochemistry, and biophysics to get functional information out of the structure that you have determined. Okay, so this is the general workflow that you might want to go through. Okay, yes.
So you said that there will be some particles that have very few, and then it's just two less, right?
Yes.
So in that word, if you just do 2D classification for them, then that will be the class that looks very awkward, right? Where there's so many noise, and reliance seems to suggest to throw those classes away. So now you're trying to say that you will try to rescue those classes. Is that the point?
Yeah. So you're talking about the spiky. You
Right.
start saying spiky class averages.
Right, sometimes. Or there's some mediocre classes, like
Yeah.
something is clear, something is not.
Yeah.
And then usually Reliant would just say throw them away. Just
So
keep
when,
them
when you
clear.
say how does Reliant tell you to throw it away? You're looking at the statistics, at the essentially at the alignment and the translation and rotation accuracy. How is Reliant telling you to throw it away? Because generally, what I do it visually, right? Going by these numbers, generally, sometimes you get great numbers and you look at the class average, and the class average is just gibberish, right? So I always go visually. Do I see features in there? And is this worth going after? And it comes with experience. But as far as coming with any sort of a metric that says good class average versus bad class average, I've always found that there's exceptions to that, meaning I've seen terrible class averages that don't mean anything, that look horrible. They get great alignment accuracy, right? So if you go by that statistic, you should keep that, but in reality, you know it's garbage. Because right next to it, you see a bunch of good class averages, and it looks like nothing like that. Okay, so what do you mean by rely on tells you to keep it or to throw it out?
No, Reliant just said that if you see the class average that
Yeah.
has some spikes or
Yeah.
some noise, then
Okay.
usually means that there's noise in there, you should throw it away, right?
Okay.
But because now I kind of see that you started to say that there are some rare fields in very few particles, then you
Yeah.
just go directly to 3D, then
Yeah.
you think that if you go for 2D, then you will, these rare few particles will belong to some junky
It might
class.
get, yeah. So, I mean, the first time I heard this was from someone from Eva Nogales' lab. So, my understanding is that in their routine, they go straight into 3D. They do 3D with Reliant, and they use a high tau number, something around 24, the tau fudge factor, and then I mean, it's in their publications. They have a bunch of these things in there. So, people have different types of strategies, and if you look more into, if you read the part that's not necessarily always fun, which is the materials and methods section, that's where you learn a lot of stuff, right? And a lot of reasons why experiments are not reproducible is because people are not reading the materials and methods, and they go, I can figure it out on my own. So it's read that part. So yeah, that's the first time I heard it. I'm like, oh geez, let's give this a try, and it helped out, right? It helped out a lot. So I mean, they use it. They have Ava's obviously has an extremely successful project group going on there. So if they're doing something right, it's worth it, you know. Okay. And then there's other things you can do with Reliant. We can, for example, ignore first zero. It's got these little flags that actually end up helping out, and we use always when we process our data. We can talk about this later. Okay. So other questions? No. How are we doing on time?
You're doing great.
Okay. Great.
Yeah, we're at 4:10,
Yes.
so you still have at least 30 minutes.
Okay.
At least.
Can I ask another one?
Yes.
Can you predict that which 3D class will have higher resolution than the other?
So if you're lucky, what you'll see is one class will have significantly more particles than the other. If you look at, for example, if you're using Reliant and you look at the model.star file, it's got the frequency, it's got the resolution, it's got all the things. You might see one class that has a lot more, and if you look at the reconstruction, you look at all of them, you'll see it actually goes to a higher resolution. You'll see a lot more features. That's the easiest case scenario. I'm working with this case right now where essentially all of them have the exact same number of particles in them, and all of them look reasonable, and they all don't look great. So then it becomes, well, what do I do? Then I'm going in towards focused classification. Let's put a mask over the part that's most consistent, and let's see if this will essentially throw out the garbage particles. Right? Sometimes it's super easy, other times it becomes problematic. Okay. Okay. So full frame processing. There's a couple of I know of 3 programs. There's a UCSF Motion Core. This one is not used as much because it's been essentially replaced by the Motion Core 2. And there's also Unblur from Nico Grigoriev's lab. So I think I know we use Motion Core 2 most, again, because of the GPU. It runs the fastest, and it's also used here, so we do our motion correction here, and we go forward with it. Again, if you have tiny particles, you might want to think about doing these additional things and doing, for example, align by each individual particle itself. But if you have big chunky things like ribosomes, large megadaltons, then you're fine doing the Motion Core 2, and you can use it has this patch option where it breaks the micrograph into smaller patches and aligns those patches. So essentially, it's somewhat of a looser way of doing something like doing per particle drift correction. Okay. And then you have per particle frame alignment, which I already mentioned. Reliant has this movie mode, and John Rubinstein's got this really nice algorithm for doing aligned parts for each particle. It takes a while to run. You need to do a lot of iterations, but again, if you're desperate and if you have the pipeline set up for this, by all means use it. Okay, be aware of everything's out there. Don't stick to one routine. Okay, you can have your bread and butter for the things you go to, but you need to essentially, the best way of doing it is be able to do single particle analysis rather than being able to do just one pipeline. Okay. Practice your creativity. Then again, obviously there's your CTF estimation. It's estimating the defocus value. Many different programs to use them. Some of them are not used. ACE, for example, EMAN is not used that much. CTF Find 4 is used here. It's fast. It's robust. It gives you good CTF values. We use GCTF sometimes. A version of GCTF allows for per particle CTF estimation, but again, Reliant does that later on. So you could, for example, use per particle CTF estimation with Reliant. Okay? Sparks, each one of these, for example, Sparks, EMAN, and EMAN2 are their own programs, and they have their own workflow that you can go through. And again, once you understand the workflow, you can start playing around with different types of strategies. Okay? Particle picking, I prefer to still pick a good number of particles by hand. Reason being is that if you're working on a new project, you need to know what the particle looks like, right? If, for example, you see, if every particle you look at looks different, then you have a problem, right? But if you see the same particle popping up over and over again, then you know that there's some sort of a homogeneity there, okay? So pick particles by hand. I generally pick 5,000, 6,000 particles by hand. It allows you to become familiar with it. It's an intimate process, and this way, when you get 2D class averages, a big problem with people who start out is that, oh, I have a 2D class average, therefore it must be correct. I have a 3D reconstruction, it must be correct. The purpose of the program is to give you something, and a lot of times that something could be garbage. Okay, so by doing this particle picking, you become a little bit better acquainted with what you're looking at. There's automated particle picking. There's Dog Picker, EMAN2. Geotomatch, Cryolo, some of these use neural networks. I think EMAN2 and Cryolo have neural networks. These, you train them in a particular data set and they become really good at picking particles. Okay. ARPWARP also has a particle picking routine. I haven't had a chance to try that as well, but that's a fantastic package to use as well. And then you also have template-based, which you give it 2D class averages. Or what you can do is if you have a 3D reconstruction, you can calculate, for example, if you get a 3D reconstruction from tomography with subtomogram averaging, you can calculate projections from that, take those projections, feed it into the template-based picking. I don't know why EMAN's on here, but it shouldn't be on there. Rely on Geotomatch and find them from Appian. Again, there's additional programs out there that will do actually template picking, and using the template that you give it, they do a better job at picking out the particles. Okay, so what you can do is you can start off with using this Gaussian blob picking, get something like 100,000 particles, do 2D class averages, get good class averages, and then feed it into this. You may actually be able to pick out more particles or a smaller data set that's actually now manageable to process. Okay, so the image classification. Many programs out there. There's Spider, iMagic. iMagic costs some money. E-Man 2, rely on. I put some of the advantages here. It's GPU, uses GPU fast. We use rely on first because I think it's easiest to write scripts for. There's Sparks that uses ISAC. This is a really good way of doing 2D class averages. If you have a particularly challenging data set, I'd strongly recommend, I wouldn't recommend, I would demand that you use ISAC. The disadvantage with it is that it requires you to have a CPU cluster, right? It's pretty hungry, and if you don't have a cluster, then you're gonna have to wait some time before it gives you some answer. But it's iterative, it's stable as the name implies, and if you have a challenging data set, absolutely go into it. So Pavel is working on this, Pavel Penchik, and he's always making it a little bit faster. So at some point, it may be on a GPU, and it may be the go-to routine for 2D class averages. CryoSpark on here, it's GPU, uses GPU machine learning. It's extremely fast, except you don't have command line interface, and it's not. Because of that, I don't go into that first. It becomes everything's done using a web interface, and for some it's a great way of doing it, and that's the only way of doing it. For me, I'm a little old school. I learned how to do everything using command line interface, and when I step away from that, I feel a little icky. So by all means, if you're okay with not using the command line interface, you're missing out on some great stuff, but CryoSpark would be the way to do it. And then there's also XMIT. And what are you looking for your 2D class averages? Here I've thrown in some, and the great thing with CryoSpark is that it keeps a record of everything that you're doing. And I think Legion or Appian was the first program to actually start doing things this way, keeping a record of all the programs that you're running, the results that you're doing. So you don't really need to take notes in your notebook, and you can just go on the website and you can just copy and paste this into your presentation, right? You don't need to dig out which job was it on, rely on that got me this result. And if you're terrible at keeping notes, and a lot of people are, CryoSpark does a really good job in doing that for you. Again, giving out the proper shots, I think, again, to my recollection, Appian was the first program set to actually do that for you, okay? And then there's XMIP, which is also a great package, and there's SciPion, which is, I guess, the counterpart to Appian. It's another program package that ties in multiple programs and tries to take notes for you. Okay? But what you're looking at for in your 2D class averages is you're looking for features and you're looking for consistency. You don't want to see spikes, and when you look at it, you want to see these tiny little features popping up telling you that, yeah, this is actually aligning. I'm getting good high resolution information. Let's take these classes. Let's throw out anything that doesn't look like this. Look at the background. The background is essentially, there's nothing there. And you can essentially, in your head, say, yeah, this looks a little bit like this. It's rotated this way and it's rotated the other way. So I'm getting consistent things back out. Okay? So these are good 2D class averages of ribosomes. Ribosomes are, depending on which sample you're working on, are straightforward, and they work out extremely well. Okay? So you want to look for features in your 2D class averages. And then, obviously, you want to go, yes?
So, Yoke was talking about how Spider is like how he learned how to use single particle analysis.
Yes.
Is it used a lot in labs now? Or is it like it's a dying?
I wouldn't say anything is dying. So Spider, I wrote a lot of routines for Spider. And just a couple of months ago, I went back to it because there's a lot of things that Spider can do that others can't. And I think that I hope it doesn't die out, and I hope it continues to be supported, because I have a feeling that some of these things that Spider can do and Spider does that others don't will eventually be useful for certain projects. Okay, so because of that, my routines every once in a while, I bring them out, I use them, and Spider is like the only way of going at it. But then you have to have grown up knowing how to write scripts for Spider. And if you can code, then you'll pick it up no problem. If you can't code, it's going to be a little bit problematic. And it's a lot like coding is a lot like doing a math problem. You go through a logical set of steps, and if you can't do that, you're going to have trouble with it. Okay? But if you want to do anything serious with single particle analysis, you really have to be able to blend all these packages to one another. So you have to be able to think like that. Okay? Other questions? Yes?
if you start seeing spiky particles, what problems are you running into?
So generally, when you see spiky particles, when the program is putting a lot of weight on your on the high resolution terms, it's pushing the resolution. So what I generally try to do is I restrict it from pushing, trying to 8 angstroms, 7 angstroms, 5 angstroms, and try to keep it from doing that. And each program has a slightly different way of trying to deal with that.
So that's an overfitting problem.
It's I would say it's an overfitting problem.
Have you ever seen difference in spikiness depending on different like buffer conditions, or like signal
Ooh.
noise ratio in the buffer?
So I also see spikiness when the signal to noise ratio is low, right? So like I said, we had a data set where we tried a 225 kilodalton particle on carbon. You could see the particles, but everything came out spiky. And I think it was spiky because it had a low signal to noise ratio. So if you have something in your buffer that affects that, and also if you have situations where your defocus value for your CTF estimations are poor, and every power spectrum is poor, and you're like desperate, you're like, oh, I'm going to process state instead, I always see spikiness for data set like that. Okay? Other questions? No. Okay. So, reference generation. Some of these, the modern ones, are obviously ab initio, EMAN, EMAN2 have their way of doing it. Sparks has, essentially all of these uses a slightly different way of doing it. Relion 3 has a way of doing it. Also, CryoSpark has it, it's not on here. And these, CryoSpark is amazingly really good at getting you an initial model. So one of the reasons you might want to go straight into CryoSpark is to get that initial model. Okay? And if this doesn't work out, you can obviously go to some of the older techniques. These random conical tilt is a phenomenal way of getting your initial model. Most places don't do this. Most places don't even have the expertise to do random conical tilts. But if you have a heterogeneous data set where you see multiple conformations, and these conformations are very different from one another, then really random conical tilt, doing it in stain, may be one of the best ways of getting at your initial models. Obviously, you have tomography with subtomogram averaging. This is a lot more involved than these two additional techniques, and you really need the expertise for tomography. And tomography, in my opinion, the programs haven't reached the same point as single particle analysis has. With single particle analysis, you don't necessarily need to know what you're doing. If your data set is good enough, you can just push buttons and get a reconstruction out. And if you're like, I don't care how it does it, I just want to get my cell paper. And you see a lot of cell papers like that, and that's fine. That's the purpose of when you automate a procedure, when you make a program that's robust enough, and when the technique is robust enough, the user doesn't necessarily need to know what's going on, and they can do their science. We see this with many different techniques inside the lab, and that's really the hallmark that a technique has really matured and reached a point where anybody who has access to a microscope and has a sample can do it. Okay, that's when it matures really. A technique is really matured and it's really accessible to everybody. And not all techniques are like that. So tomography is a little bit different in the sense that the learning curve is a little different because it's not as automated. You really have to know what's going on. And a lot of the programs, for example, Dynamo, reminds me of how Spider thinks and how Spider used to work. So I can make that analogy and I can understand Dynamo a little bit faster than someone who's just like changing variables and trying a couple of different things. So knowing some of these older programs, for example, Spider, and then it actually helps you out with the tomography aspects as well. So different ways of doing tomography. One program that's not on here is EM Clarity. That's supposed to be the latest and greatest. That we have that running, so let's see what EM Clarity is capable of. Again, by doing all of these programs, by knowing how this thing works, you can again get creative, take many different routes at getting your final reconstruction at the end. There's tilt pair test. This was essentially a way of assessing whether your reconstruction is correct or not. But I think with nowadays being able to get to atomic resolution, you have biophysical results or information coming out of a reconstruction, so you know that it's correct. There's no way you can get the molecular envelope of an arginine and have a wrong image reconstruction. Okay? You can no way see helices and beta strands and go, well, there's something wrong with this reconstruction. If there was something wrong with it, you wouldn't get to that resolution. So just getting to that resolution is essentially or seeing those features is indicative that you're on the right path. And again, machine learning is being included in a number of techniques, and this is, again, going under the hood, making things a little bit easier, making it more of a black box, at least for me, because I don't know exactly what the heck machine learning is doing. Okay? Questions? No. All right. So this is essentially what you get out of CryoSpark. It's ribosome. Ribosome is super simple. I'm just rotating it. But if you look at it, you'll see there's a funny feature going on. I'll get back to that later. Okay? So again, if you have good data set, if it's something large like a ribosome, you can get good 2D, good initial model out of it fairly quickly. So this, we're looking at 3D classification, right? You took the data that made it past 2D classification, it gave you an initial model, you plug that in, and again, this is coming from CryoSpark. I asked for 10 different classes. This is coming from Relion. I asked for 10 different classes. And you're starting to see things that look like this, right? This looks like it's a ribosome right next to the whole of a grid. I guess there was enough ribosomes in there to allow you to see something like this. This is some sort of maybe an ice, but as you can see that the 2D classification wasn't able to get rid of all of this, okay? So doing the 3D classification will actually clean up the data set, and you start seeing 50S particles. This is from a 70S ribosome. You start seeing 50S, meaning that there's 30S somewhere maybe in the data set or maybe in the ice that you didn't pick and you didn't extract out of it, okay? So there's many different 3D classification ways, programs to use. Again, Relion, XMIP, which is the predecessor to Relion. There's Freeline and System. I particularly like Freeline for doing focused classification because it seems, again, in my hands, it does a lot better than Relion does. Maybe it's just in my hands. And it's fast, and going back from Freeline back into Relion is fairly straightforward. System is supposed to be better than Freeline, but this is GUI based. Again, I'm old school, I'm slow to learn new things, so I stick to Freeline until this is made possible to write a script for it. I just haven't had the time to do it. Okay? So again, many different ways of doing 3D classification to further clean up your data and to start seeing conformational changes. For example, you can see that this part is a little bit different than this part, and it's a little bit different than this part. And then now you can, for example, take just these particles and refine it against this to push the resolution. Okay? So pulling out conformational heterogeneity. Okay? So again, here we took all of these good particles, combined them into a single stack, and then started doing focused classification and things like that. But I'm not showing that. And again, you start seeing, for example, here there's a tRNA here that's not present in this reconstruction. Here it's cocked down a little bit. So again, you start seeing pulling out conformational differences, and you can see some of them go to extremely or high enough, better than close to 3.2 angstrom resolution, and you can start getting out atomic information out of that as well. So this is the refinement part for whether you do this after focused classification or before, but you can once you get to this and you start pushing the resolution again, there's many different types of programs that you can use. CryoSpark tends to be one of my more favorite part for this programs to use for this part because it's so fast. And for whatever reason, in my hands, it seems to be doing a better job with dealing with anisotropy than something like, for example, Relion. So I'll talk about anisotropy. Any questions so far? How are we doing in time?
15 minutes.
15 minutes. Okay, I'm almost done. So you have your map, you have your high resolution. The FSC says something like around 3.2 angstrom resolution. And even with crystals, you have crystals that diffract to 3.1 angstrom, 2.5. But then whether are you really at 2.5 or you're not at 2.5, there's many criteria that goes into it. And at the end of the day, within that structure itself, you're going to have a wide range of resolution. So for here, you can do local resolution with EM, where here in the blue you have about 3.1 angstrom resolution, and out here in green you have something like maybe 7.3 or 5.9 angstrom resolution. Okay, so the resolution varies, and if you guys have done crystallography, this would be almost similar to a B factor, right? You can, in the core you have low B factors, and in the periphery you might have high B factors. And in situations in crystallography, you'll have a loop. You might be even at 2 angstrom resolution, and you'll have a loop but you have no density for it. And that's because it's either it's flopping around or you can't identify the density. So the local resolution to me is similar to what you would get with crystallography, right? You have high B factors because it's a low resolution. You don't, it's flexible and you're not getting high resolution information out of it, okay? So these nowadays are really extremely important. Obviously, these manuscripts want to see things like this because you might say 3.1, but you might have a large portion of it that may not be at that indicated resolution. And at the end of the day, what is the resolution that you really need to be at, and what is the story that you're trying to tell? Okay. Again, multiple ways of doing local resolution: ResMap, LocRes from BROS. There's MonoRes from XMIP, one of the newer ones. And what you can do is, if you have regions that have, for example, that are lower in resolution than those in higher, it might indicate that you have conformational flexibility here, or you might have configurational differences there. So you might want to put a mask here and do focus classification. You might pick out different states, and each one of those states may actually go to a higher resolution than the parent, because you might be averaging multiple states, so you have a low resolution molecular envelope for that particular region. Okay, and then you can do variance estimation, and if you have a good structure, it's homogeneous throughout, you're not supposed to get much variance coming out. And if you have a structure where you have a lot of variance in a particular region, that's indicative that there's differences there. You might want to put a mask there and do focus classification there. Okay, further teasing out information out of your data set. So here, anisotropy, we had problems with one data set with ribosomes, and I think this is a general trend with ribosomes, in that you get preferred orientation. Okay, so again, this is just pulled off of Cryo-SPART. Here you're looking at your SFFSCs. This is somewhat similar to what you might see for X-ray crystallography, your reflections coming from your diffraction. If, for example, you have a circle here, that's indicative that there's no anisotropy and everything's isotropic. You have resolution. In this image, everything is isotropic. But as you can see, as you rotate the image reconstruction here and here, you can see that this circular feature, you start seeing wedges in here. And this becomes elongated. And this is indicative that you're missing particular types of orientations. Okay, and then you also see that in the elongation of the density as well, right? So here everything looks good, and here you can see that the density is elongated. Okay, so when you...
I have a question.
Yeah.
How do you know that that's anisotropy because you don't have the view, and it's not because that particular domain is like super flexible or something? Is there a distinction? Is there a way to know that?
Yes.
Quantitatively?
Yeah. So for example, if you have a domain, so here for the entire map is elongated.
Okay.
Right. So if the entire map is elongated, that's indicative of a global feature.
Got it. So
But
that's
if you have-
preferred orientation.
Yeah.
Okay.
If it's a local feature, it may be, and in this data set, this is one of two different types of ribosomes in this particle data set. The other ribosome essentially had no preferred orientation. Everything looked good, but this one has a particular subunit present, and this one gives us preferred orientation. Okay, so it's not something of the global entire data set, but it's something about that particular particle type. And so if it's local, if it's a local feature, then it's probably going to be something again. It could be flopping around. Also, with the flopping around, what you'll get. So this would, for example, be a flopping around kind of region.
Mm-hmm.
Whereas,
Like if I were to just look at that,
Yeah.
I would say like that just looks like a flexible domain or something.
so you could put a mask on that and see how it does.
Okay.
Do the focus classification on that. Okay? So one of the things I've noticed with ribosomes is that, for example, in a lot of the papers where they publish, for example, we put all of our data into all the data that survived the 2D classification and calculated 10 3D class averages, and out of these 10, only one was good, and that's composed of maybe like 7% of the particle data set, and the rest are bad. To me, as biochemically, that's always been a little bit troubling, because that means that 95% of what was purified was garbage and only 5% was good. And I think a lot of it has to do with only 5% of the data sets survived anisotropy. And I think the 3D classification is actually pulling out isotropic data, preferred orientation, and the rest is actually the data that does not have any preferred orientation. So I don't think it's a biochemical thing. I don't think it's a bad particle thing. I think the 3D classification, at least with a couple of examples that we've had, is actually purifying or dealing with the anisotropy problem. And you can imagine that, for example, this will give you a good reference, whereas this at a lower resolution will give you a smeared out reference, right? So when you're trying to align particles to a smeared out to a bad reference, for example, if one model was more anisotropic than this, then all the garbage is going to go into that, whereas the rare views are going to go into a reconstruction that does not have the preferred orientation, right? So as you're purifying the preferred orientation out, you get a better reconstruction that has less anisotropy present or is more isotropic, and that gives you better references. So the few particles that have that rare view are going to align to it better. And as you iterate through this, you're essentially fishing out the rare views. Okay, so 3D classification could actually be used to clean up, to deal with anisotropy. Other ways of dealing with anisotropy, obviously, is using the tilt strategy, where you essentially collect data at multiple tilt angles, and these gives you additional views, and with the additional views, you can essentially deal with the anisotropy. Okay, spotted on is supposed to be good with dealing with preferred orientation. That's another strategy, and you can obviously combine the two of them together and collect. Do a spotted on and then collect at multiple tilts as well. So generally what we do is, if we work with any sort of a ribosome project, we're going to collect 0 degrees and we'll collect 15 degrees, half on each, and then process that, and hopefully there won't be any anisotropy. And if there is, we'll collect another day at 30 degrees. Okay? Yes?
So you will keep doing the 3D classifications a couple times.
Yes.
To fish out the anisotropy.
So you could do that. So you could do, your first set is to clean out all the bad particles that essentially survive the 2D classification, right? To get rid of, for example, these guys and even that guy, okay? And then you take this, you could combine these together, and you can start doing that, doing multiple times to essentially fish out the rare views and put all the rare views in one group. And hopefully all of those have the same configuration and some same conformation. The best strategy, obviously, is to go back and collect more data, right? But if you don't have time for a scope, and then all you can do is play with the data, is take that strategy. That's worked for us to a certain extent, but we had to go back and we had to collect more data. So sometimes things will go only so far. Okay? Other questions?
When you collected multiple angles, do you see difference in contrast depending on like the difference in path length?
Yes, so obviously as you tilt more, you're going to see less, your ice thickness, your beam has to go through thicker ice, and you're going to see less contrast, and also your particles may start overlapping on top of one another.
I guess you account for that somehow in your reconstruction process? Or can you combine those data sets?
Yeah, you can combine the data sets, that's the idea.
Do you have to compensate for the difference in contrast, or will the programs automatically?
I don't believe you have to compensate for the difference in contrast, because Relion does some scaling itself.
Oh,
because you're
okay.
looking at each particle itself, you're not looking at the entire micrograph. I think you're fine in that regard. I don't think you have to use special tricks. Other questions? No YouTube questions?
That was the last YouTube question.
Okay, great.
All right. Well, let's thank our speaker for coming in today, giving us this lecture.
Thank you, guys.
Obviously, follow up with any questions if you guys have any.
So would you keep any particles that will contribute to your angle distribution, but not the resolution? Would you keep any particles that were contributing to your angle distribution, but not your resolution?
Absolutely.
Yeah.
Yeah. Because what you don't want is you don't want a 2 angstrom data set of
In
one view.
Yeah.
What is that good for? Right? It used to be that if you had a membrane protein, you had that one view, ooh, that's a big paper. Nowadays, it's like, yeah, that's nice, buddy. Right? So you want to keep that. Now, if you can replace it with better data, obviously you want to replace it with your better data. But when you look at, for example, when you look at that reconstruction that I showed you, this one is anisotropic. CryoSpark says 3.4 angstrom, right? And you look at it, the density is elongated. So it's going to take someone who's experienced with looking at molecular envelopes to actually be able to really interpret that very well, right? So if I had additional views that did not contribute that much to high resolution terms, I would keep them in there, right? So because it's saying that, again, at 3.4, you should be able to see everything you want to see. But because it's anisotropic, it's not really at 3.4. This way it might be at 3.4, but this orientation, again, you see this with crystallography. In crystallography, you have anisotropy all the time. It's not at that resolution, so you really, the interpreting it and building in an atomic model becomes really problematic and questionable. Okay. All right.
All right. Thanks again. What is next Wednesday? That's journal club? This Wednesday, sorry.
Yeah, so this Wednesday we'll be having a practical, a single particle practical. So everyone just bring along, whoever wants to come along, but just bring along a laptop and try to install a camera on it. We'll be doing the icky stuff which we'll talk about. We'll be doing Cryo-Sparks, yeah. And we'll be doing it on the cloud as well. So just bring along your laptop, everything will be up there. And install a camera so you can see stuff. Yeah. Everyone signed in, right? So